Welcome to another mathematical moment from the American Mathematical Society. I'm Scott Hirschberger. Today, I'm talking with Dr. Rodney Kizito, a technology manager for the U.S. Department of Energy's Solar Energy Technologies Office. He's going to tell us about the mathematics involved in connecting solar power to the rest of the electric grid. So, Dr. Kizito, welcome. It's great to be talking with you.
Great to be talking with you also. Thanks for reaching out and for providing this opportunity for us to have this chat today, Scott.
Certainly. So to start out with, I'd like to talk a little bit about how the electric grid works right now in the US. What's the background of just like how electricity gets generated and comes to our homes?
There's three aspects that come to electricity generation in general, or how we ultimately get electricity in our house. So there's the generation end, which is the power plants that actually generate all the power, and some of those are still, natural gas and coal-related ones. And of course, there's the recent growth of solar and other wind generating plants as well. And then from the generation end, you go to the transmission. So once the plants generate the power, this power is then transmitted across, long transmission lines that you can see on highways and whatnot. And those then get that power into the local areas. And then at that point, it's now on the distribution end of the grid. And that's where the power that's transmitted from those plants is then distributed to the different houses and businesses and other aspects that use that power within, the general communities and cities and towns that we live in.
Okay, awesome. So now let's say I want to hook up some solar. I want to put solar panels on my rooftop and have them providing energy to my home. How does that energy get integrated with the energy in the rest of the traditional grid?
Gotcha. Yeah, so the application of solar, especially rooftop solar, to homes and businesses and such, works with something called an inverter, right? So you have the solar system or the solar panels, which you can place on the rooftop, and those then take in the energy from the sun and translate that into the power that you're going to be using inside your house using that inverter. So when the power comes in from the sun, it comes in as DC or direct current. And that's then converted to AC, which is what makes it more suitable for the appliances and different things that go on within a house. And then once that's done, that you can utilize that power. And if you happen to be producing more power at that point, then your house or your business has demand for that power. Then some of that power can then be converted back into the grid and sold back to the grid for usage elsewhere.
And as far as that selling the energy back to the grid, from what you were talking about at the beginning, it sounds like traditionally power is flowing just one direction from where it's generated to the homes and businesses. So what happens when now we're trying to send power the other direction, like from a home back into the rest of the grid?
Gotcha. Yeah, so that's actually one of the things about our grid that, the Solar Energy Technologies Office, or SETA, that I work with is doing a lot to help sustain and be able to really, really make happen. Our grid is set up for unidirection power flow from the generation to the ultimate end user. It wasn't originally designed or constructed for bidirectional power flow. But there are a lot of technologies that have been developed over the past decade plus, such as like net metering, which does allow you to then be able to send whatever excess power you have back to the grid as well. There's still further improvements that are happening through this with different types of inverters that are being created, different types of protection schemes that are being put out there to make sure that the grid is ultimately stable to be able to handle this bidirectional power. But in essence, that's how it happens.
Okay. So what sort of mathematics is involved in trying to model those situations and make sure that energy is actually getting used and not wasted?
Yeah, well, math, the beauty about math is you see math in everything, right? There's nothing that happens in this world that doesn't have some aspect of mathematics applied to it. And it's the same thing with power, right? In our power grid. So when making sure that all that goes down the way it's supposed to go down. There's different ways you can approach it. Some of them are it's the usage of mathematical formulations and mathematical programming through the use of things like linear programming and methods like operations research, which allow you to take all the different variables that come into play when it comes to how power works and how power flow works and formulate those as mathematical equations, which then allows you to ultimately capture the entire power grid as a system and how it's supposed to work. And through that, you can then run different, optimization things, as they call it, right? To try to maximize how much power is being utilized, to try to minimize how much power is being wasted. Math has developed a lot over the years. It continues to develop every time too. You can go in there and just program a code that basically can then take what's happening within the system and run multiple simulations on that a lot faster, and be able to handle a lot more variables than some of the traditional operations research and mathematical formulation type approaches can.
Cool. So when you're setting up those simulations, would it be correct to say that you're still coming up with a set of equations as a researcher to try to model what's going to happen, and then you're giving those equations to a computer to see how things play out?
Yep, and in both aspects, you are coming up with equations and giving them to a computer to see how things play out. The difference with simulation is there's softwares out there which can add like actual visual representations to the mathematical formulation of the system that you've made.
So when you say visuals, are you talking about like a diagram of the system and something showing like where power is flowing and how much power is flowing?
Yep, so when you get the diagram of the system, you can put the generation sources, the actual plants themselves. You can add in there the feeders, which are going to be the lines that actually send power from one generation point to the ultimate end user side of it. And you can add the substations that, take the power and change the voltages to match whatever voltage is necessary, whether it's the voltage necessary for transmission across long highway lines or the voltage necessary for distribution into Scott or Rodney's home, right?
So one direction I know things are headed that seems to be kind of exciting is this idea of solar microgrids. So could you explain just what those are?
Yep, so microgrids in general are just a smaller sector of a larger grid that's able to operate on its own, that doesn't rely on the regular generation sources that the larger grid relies on, right? So the microgrids usually incorporate distributed energy resources, as they call them, or DERs. And those DERs could be solar-based, they could be wind-based, they could be hydro-based, it could be storage technologies that are put in there. But ultimately, that microgrid just allows you, it provides you a separate power source within the larger grid as a whole, to where if something is to happen to the larger grid as a whole, this minor, smaller power source within the larger grid can still function.
Okay. Can you give me a real-life example of when a microgrid has proven successful, maybe after a natural disaster or something similar?
There was one out in Japan when Japan experienced that heavy earthquake in I think it was 2010, 2011. There was a hospital and a university in there that already had a microgrid system set up that was able to then kick in and help provide power to the hospital and the school campus when the earthquake caused the tsunami, and the tsunami came through and wiped out a large portion of the downtown area's power grid in general. That area was able to continue functioning because that school and the hospital did have that microgrid set up to operate there. And then there's some other ones that we have even worked on as Kizito directly that we've helped fund. One of them was a microgrid in the Bronzeville, Chicago area. Now, Bronzeville is a historically black area, and when a lot of these major disturbances happen on the grid, especially caused by natural disasters and storms and such, low income and minority communities such as that Bronzeville community typically end up facing a lot of the heaviest impacts when it comes from a lack of resources that those communities have in general compared to more well-off communities. So that microgrid out there, they just finished final testing on that a few months ago. So that one should be going live pretty soon. That microgrid has a combination of solar systems and energy storage systems in it. And it utilizes rooftop solar, and it ultimately provides a sense of support and resilience. So that kind of approach of community microgrids, which the Bronzeville project that I'm talking about now is really helping show how that can work in the U.S. The goal is for that kind of approach to be expanded across the U.S. in general, because there's a lot of communities that could utilize such microgrids in general across the U.S.
Yeah, that sounds like it'd be great, because then you're reducing dependence on a larger grid and making sure everyone has access to the resources when they need them.
Yep. And then the beauty of the microgrids too is, when the main grid is fully operational and there is no disturbance on there, the microgrids now serve as an added power source to an already powered area, right? So now when you have more power supply available, what does that do? That can trickle down to less costs for power and electricity for the common person.
Can you talk a little bit about what you've been working on most recently and what you enjoy about working in this area?
Gotcha. Yeah, so well, I guess I'll start with what I enjoy working in this area. So, power and power supply and renewable energy in general, especially solar, it has a bit of a personal connection to me. I'm from Uganda, a small country in East Africa, and we have less than 30% of our population that has access to the country's power grid. Why? Because most of the country is rural. You don't have transmission lines and distribution lines stretching out to some of those far out villages. But what you do have is the sun. You have an abundant resource in the sun. So I kind of realized that, okay, if I'm going to be studying this engineering thing, let me be involved in something that I think ultimately I can utilize later in life to try to impact and give back to my home country back home in Uganda. That's why I love working where I work at. And some of the recent things that I've been working on, we just recently finished the Solar Forecasting Prize, which was a prize that we developed to try to incentivize end users within the solar forecasting community to develop and utilize what they call probabilistic solar forecasts. And that's the forecasting of how much irradiance is going to hit a certain area of the Earth at a certain time period in advance. So the prize was focused on day-ahead solar forecasting, which as a grid operator, that's beneficial for you because it allows you to know how much solar radiation you're going to have a day ahead, and by that, you can then compute how much solar power you should expect to have at that time. And now that you know how much renewable solar power you'll have, that allows you as a grid operator to then be able to plan better how to maximize and utilize your power assets that you currently have now, knowing how much power you'll have at that time period in advance. It was a great competition. We had about 23 different teams that competed. We ended up giving out 5 winners, 5 winning teams, and then 2 teams that earned runner-up prizes. The winners earned $50,000 in cash prizes, and then the runner-ups earned $25,000 in cash prizes.
Cool. So is the idea then that the winners will now go and use that money to continue developing their ideas and try to bring them into reality?
Yep, that's the game plan. Award them this kind of money. As part of the competition, we also had them submit commercialization plans, which was their ideas and approaches to take what their product is as a forecasting model and then commercialize that into an actual forecasting product or service that's available in the market.
Do you have any words of advice for students who may be interested in learning more about solar or the electric grid in general and how to use mathematics to kind of build a better future with it?
This is an exciting time in life. Our generations as millennials and the Gen Z generation behind us, and whoever's going to come after them, we're at a really great point in transition that's happening not just in our country but in the world in general. This push and move towards more clean power, more renewable energy resources, and what that really opens up is opportunity. So I would really encourage people, anybody in high school, middle school, all the way down to elementary school, dive into this right now. You have a chance to learn things regarding renewable energy that a lot of people didn't get a chance to learn when they were your age. Why? Because these weren't ideals at that time. These weren't technologies that people were thinking about at that time. So you'll get a chance to come out of high school on a much higher stance in terms of understanding what goes on with some of these things, and having learned this for so long, growing on up all through your K through 12 career, that by the time you get out there, there's going to be so many opportunities waiting on people within the solar industry, renewable energy industry, that the more you dive into it now through your K through 12 time frame, the more opportunities will be available to you when that time comes up.
Awesome. Well, thank you for that inspiring message, and thank you, Dr. Kizito, so much for talking with me. I've learned a lot.
Absolutely. Thank you so much once again for giving me this opportunity today, Scott.